First, the gyroscope is nothing like a rock on a string, because you will not get a resistance force from a rock on a string. This is going to be about causality, which is more than just describing what you see it do. This is engineering simulator software that is far more capable than mere velocity and acceleration vectors. But velocity and acceleration vectors are all I need to present the causal components of the gyroscopic effect. It's crazy that I feel like I have to say this again, because most people show you what it does and they act like they understand it. I'm going to show you what actually causes what it does. Did that sound weird to you? Because that language is lost in modern science. Physics is 100% math, and math can miss causality completely and still give the right answer. This simulation is two different views 90 degrees apart of a single tilting disk. This disk cannot precess because the yellow and blue tilt axis is anchored to prevent it from moving beyond tilting. The disk can only spin about the spin axis and tilt about the tilt axis. This is the cause of the gyroscopic effect right here, and it hasn't even begun to spin yet. The red vectors are tilt velocity, and notice that the amount of tilt velocity depends on its radius from the yellow and blue tilt axis. A small torque was required to create these tilt velocities, but it wasn't any more torque needed than for the moment of inertia normal to a flat disk, mr squared over 4. And this is true for spinning or not spinning. Don't jump ahead to the resistance force because you don't understand yet. Just wait. Now spinning begins, and notice that tilt velocity is still the same as it was before, but now there are all of these green acceleration vectors present. These acceleration vectors are the inertial reaction to a changing velocity. The red tilt velocity vectors are a condition of the tilting plane. The tilting plane is a stationary condition, while the disk spinning is a condition that happens inside the tilting plane. So mass in the disk has to transition through these differing tilt velocity conditions of the tilting plane. The tilting plane, being like a seesaw, causes the mass inside the tilting plane to totally swap tilting in velocities every half of a rotation. A key thing that I need you to see here is that every instant is a step of change in tilt velocity that creates a brand new acceleration vector. At the extreme seesaw ends, there's an instant of pure velocity with no acceleration. But every instant after that, from here all the way to here, a brand new acceleration vector is produced with each instant of tilt velocity change. Every instant is totally resolved. Every click totally resolved in a brand new acceleration vector. Let's follow this one vector. This is just this half, and in the next half it is all the same thing in the opposite direction. It is a seemingly small velocity change that has to happen in half of a spin rotation. The reason that the acceleration vectors have differing lengths has to do with the changing radius from the tilt axis. Tilt velocity step changes are smaller steps out here at the ends due to being more parallel to the tilt axis, therefore smaller accelerations. Tilt velocity step changes that are passing orthogonally through the tilt axis are the largest steps in change, so they are the largest accelerations. Notice that they increase and decrease linearly with the radius to the tilt axis, creating a vector field. And there are two vector fields that would seem to cause a torque across the disk. These vector fields are why I split the tilt axis yellow and blue. This is the force production mechanism that causes 100% of the gyroscopic effect. After spinning began, the moment of inertia for the disk didn't change either. This disk cannot precess, so a resistance force is not going to happen. So the torque required to make changes in the tilt velocity is the same whether it is spinning or not according to this data. The reason this force looks doubled is because it must stop it and restart it in the opposite direction. That's 2. One note. The mass actually reacts to its acceleration vector as if the acceleration vector is pushing backward into the mass. These acceleration vectors cause precession motion, and they are the resistance force as well. It all happens in a sequence that you haven't seen yet. But before we move on, I need to destroy the conservation of angular momentum for you. These seesaw tilting end velocities completely swap sides twice per rotation, and every instant is a completely resolved condition of acceleration production. All of these tilt velocity vectors are tangential to the tilt axis. That means that they can never be anything but perpendicular by being a condition of the plane. Therefore, they cannot reach spin velocity from a perpendicular perspective. Yes, there are complications elsewhere, but not with these components that are always there, always perpendicular, and are always 100% causal. This completely ruins your conservation law, because now there's no need for it. Spin momentum is safe from these causal components of the gyroscopic effect. I almost forgot about the magenta vector here. This is the magnitude of angular momentum. I had to present it with the spin velocity vector, the black one, just so you could see it move. It pretty much switches sides. This simulation has the disk spinning into and out of the screen, and it has the spin axis of the disk running parallel with your screen. The acceleration vectors produced are parallel with the spin axis. I can show you another example of this acceleration production mechanism where the accelerations are oriented the same as they are here, pushing mass up and down due to the tilt velocity, but the spin axis is displaced. Just imagine this chain is the edge of a spinning disk running into and out of the screen. The lower chain is the closer edge of the spinning disk, and the upper chain is the further edge of the spinning disk in the previous simulation. The tilting is the same, the accelerations are the same, but the spin axis is not the same, because here the spin axis runs into and out of the screen. Tilt velocity causes accelerations in both scenarios, and the rate for the tilt velocity differential is the only part of the spin axis that plays. You know, A equals dv over dt. So dv is tilt velocity and dt is spin rate. This is the next step in causality. After you accept the force production mechanism that obviously causes a motion called precession, now we can let a gyro go and watch what happens. This gyro will spin without friction forever, and it is always coasting in the spin axis. The green ball is a pivot that will not spin, but it will precess and tilt with an adjustable friction parameter. The first 0.15 seconds has no friction. Then friction is turned on for most of the descent, and then at the bottom, friction is rapidly turned off. The causal vectors are the same as before. There's one major concept that you need here. A tilting plane can only have one tilt axis due to tilting, but that tilting direction can change. In this setup, there's one pivot point at the green ball. So anywhere that the disk goes will create a tilting spin plane that now has a magnitude and a direction. The tilt axis is part of that tilt direction change. Think of the yellow and blue tilt axis as the axle of a cart. The axle is always perpendicular to the direction of the cart. This light blue vector is a tilt direction vector. Collinear with it is the velocity vector of the wheel's center mass. Any motion of the disk is also tilt direction, and the axle of the cart will remain perpendicular to the motion direction. The wheels on the cart are odd in that one pushes up while the other pushes down. This analogy may not work so well because there's plenty to be confused about, but it places the yellow and blue tilt axis where it needs to be, like an axle. One last thing about the light blue tilt vector is that it is only collinear with the velocity of center mass because there is a single pivot point at the green ball. At the very top, you can see the effect that gravity has on the system. These acceleration vectors are indicating the pull of gravity. As we let it fall, the fall is a tilt direction, and a tilt axis develops. That tilt axis is producing acceleration from the tilt velocity differential. The acceleration vectors created by this tilt direction are pushing out here and in here. This is obviously creating the torque needed to begin precession, just like we expected. As it progresses further, you can see that the acceleration production is growing, and the tilt axis of the disk is starting to move to the left. The tilt axis, just like an axle, is starting to steer to the left due to the tilt direction of the disk being motivated to move that way. Remember that this entire half of the disk is producing acceleration that is pushing outward here, and likewise, this entire half is pushing inward. These halves have moved to where they are overlapping with the force of gravity. This should start to look like the cause of the resistance force to you. It is the force production mechanism slowly being steered to overlap with the force that caused all of this in the first place. The acceleration experienced as resistance is slowly increasing as the halves continue to align the tilt axis with gravity. It continues to steer itself to the point of level precession. Level precession pretty much indicates that gravity has now been overcome by the force production of the tilt axis, which is the resistance force, and the gyroscope is probably producing more force than gravity because the gyroscope appears as if it is beginning to steer upward against gravity. This is known as nutation. Nutation is the final throes of the force production sequence as the mechanism continues to steer itself to some end. In this case, that end is back to the beginning potential with no motion, just like it was when it started. If you were to push this gyro upward, the tilt axis would continue to steer itself clockwise up and over the top to begin falling due to gravity. I'm not going to cause that here, but you can imagine the yellow side of the tilt axis pushing out and steering its way over the top. Here, the gyroscope starts to fall again, just as it did before. The path that was just traced out by this gyro is a cycloid path. It is only a cycloid because there was no friction anywhere. A cycloid path indicates a 2-to-1 ratio of something. In this case, it is everything. The horizontal precession velocity is twice the fall velocity achieved by gravity, and the force produced by the tilt axis is twice the force of gravity. This 2-to-1 condition is only at the perfectly horizontal position here. Everywhere else, it is either increasing or decreasing. I will prove this in another simulation where I double the force on a gimbal and the tilt axis freezes in place due to creating an equilibrium condition. Friction is turned on at 0.15 seconds and soon a dampened equilibrium condition is achieved. There is a descent angle. There are two main irritants for the gyroscope here, gravity and friction. The precession velocity is used against gravity, and this descent angle is used against the friction in the green ball. You can see that the descent angle exposes a wedge of acceleration vectors that will create a torque, which serves to push against the friction. As long as acceleration from gravity and friction are neutralized, there's nothing but velocity. This is what equilibrium looks like. It is as if the gyro continues to steer itself into a constant velocity. At the bottom, the friction is rapidly turned off, and this exposed wedge of acceleration has a split second to accelerate precession. And without friction, this creates an oscillation around the perfect precession velocity, which is never achieved because it keeps overshooting it. If I had reduced the friction more slowly, that perfect precession velocity could be achieved, and it would go on forever at a constant latitude. When the spin axis is inclined or declined, both gravity and the force production at the tilt axis are reduced by the same scale. So if gravity pulls at a 60-degree angle, that's like half of the torque effect due to gravity on the gyro. And that angle in the tilt axis is also at that same angle. So it produces half of the tilt axis force at the same precession velocity. That's why the precession velocity stays relatively the same all the way down. It does slightly change for other reasons, but they are small reasons above and below level precession. The lower left box is the input force being shown constant and then being doubled. And the right one is, well, there's the input force with its path. But the right box is the velocity of that input force as the middle curve. The outer curves that are doubled are the precession velocities. This is a gimbal gyro that shows a constant force pushing on the frame, causing the gyroscopic effect. The small green arrow here. You can see the path of the force here. The first time the tilt axis passes through, creating what we talked about already. The second time the input force is doubled, precisely at the arrival of the tilt axis. This merely instigates an equilibrium condition with the force doubled. At this point, everything is coasting because all of the forces are opposed and therefore cancelled. Nothing is holding anything. It is purely opposed forces that have nowhere to go. I've spent an embarrassing amount of time trying to find a way to exploit this doubled force. Any attempt to exploit it destroys it. The most amazing thing with this simulation is that when the force is turned off here, it is like the gyroscope is set free, and it wobbles. Wobbling is a gyroscope, uncontaminated by external inputs. The physical default with only the gyroscopic mass without friction or dead weight is that the tilt axis turns 2 to 1 compared to the spin velocity. Of course, with friction and dead weight, the tilt axis courses through the system at much slower speeds, and it can be slower or faster than the spin velocity of the wheel. This simulation is another restricted gyro that cannot precess. It is different in that it has a magnitude of velocity and a magnitude of acceleration coming from each of the 12 coordinates. This lower right window shows that spin velocity and tilt velocity are component vectors of a magnitude of velocity, here. This magnitude of velocity follows a path in space, and that path creates a rose pattern. The blue path of the blue coordinate is a rose pattern with 3 petals, because this blue coordinate is spinning 3 times per 1 tilt revolution. The number of petals in the rose are due to the ratio of spinning to tilting. This is the basis of my math. Describe that rose pattern path and take the second derivative. The second derivative gives the acceleration experienced by following that path. This is independent of mass, which is very interesting at first, but the radius and density of the mass creating this acceleration is very important in terms of force. This simulation contains a lot of extra information, such as the fact that a 2-bladed propeller can affect its spin velocity by tilting, because there are components of the accelerations that cannot cancel like they do in a disk. It essentially wants to sling the blade to be orthogonal to the tilt axis. This gets into the fact that both spin and tilt velocities are tangential to their respective axis, which means that they are both changing directions. This is just a small added feature to everything I've described thus far, but across a disk, it all cancels with itself. We've already seen these acceleration vectors, and until now, you've never heard that they create a cylindrical hoof shape coming from half of the disk. You can see it in these vectors, but they do not illustrate the midsection very well. I've turned on some extra vectors that can show that there is a flat plane to this cylindrical hoof. The flat plane extends from this line at the diameter of the disk, and it runs out to the cylindrical outer surface of the hoof. Notice how the vector field straddles the tilt axis. It's very interesting that these acceleration vectors are theoretical, and they don't need mass. I think this is a significant thing that is missed in physics today. Acceleration is an absolute, and all observers agree on accelerations. There's nothing relative about it. Inertia is absolute. I think that mistakenly thinking in terms of relative aspects has physics clinging to reference frames to make sense of something that doesn't even exist. Think in terms of absolutes and relate that to space. Huge tangent. I'll come back to that later. This is my paper. The math technique is to integrate the hoof shape with the mass density that created it to make it a force field with a centroid. That centroid is the basis for calculating the needed force to hold the gyro up as a normal vector to the spin plane at that centroid radius dimension. That needed force number, normal to the spin plane, ends up being the mass of the force field. I describe the rose pattern path with these parametric equations. Then I take the second derivative. This gives 4 terms in x and y each. 2 of the terms describe the radial acceleration to the respective axis in the term, and 2 of the terms describe the acceleration vectors that are normal to the spin plane, and they are added together. The description is restructured to describe from the perspective of the mass to read acceleration equals 2r theta phi. This looks like a Coriolis force description. The next step is to analyze the density and radius of the mass that would produce acceleration in the gyro. Group the mass in the gyro by an inner and outer radius of a particular density. Each density group has a factor that is the width of that mass in the gyro times the density of that mass. Here, number 1 has an inner and outer radius, a summed width of material, and a density of plastic. Number 2 has an inner and outer radius, a summed width of material, and a density of iron. You get the idea. Now, integrate the cylindrical hoof shape of acceleration vectors with that density factor, which is width times density. The gyro here in the paper needs 5 hoof shapes to cover the density distribution in the gyro. The hooves all overlap and share the same flat plane beneath them. However, their outer radius depends on the radius of the mass that created them, so the shape of the hoof will reflect that density. All 5 hooves are added together. This infuses mass into an acceleration field, which makes it a force field, because force equals mass times acceleration. The benefit of this is that it now has a centroid dimension that is the center mass of the force field. As the length of the field changes, thereby becoming more force, this centroid radius dimension does not change, so it becomes possible to calculate what force you need from the gyro at the radius dimension. Triangulate the linear force that you need to push into 1/2 of the spin plane as a force. This means take half of the unbalanced mass that creates the gyroscopic effect. This is either the weight of the gyro or it is the weight hanging on a gimbal causing it to tilt. Calculate that halved weight around steps A, B, and C and D to get the required linear force normal to the spin plane. The next steps concern integrating those hoof force fields and adding them together to get the centroid dimension. Initially, you have to create a unit force field with Hmax set to 1 in the entire group. Once you're at this level, divide that linear force that you need at the disk by that unit hoof mass value, and this gives the acceleration vector at the largest center vector. You don't have to go any further because now you have everything you need. That vector is described as that acceleration is 2r theta phi. So just set these equal and calculate what you want. The r will be the Rmax value, but spin and tilt are a combination that you can calculate. It works. I'm not even a mathematician, and I put it into an Excel spreadsheet with simple formulas, and at level precession it is very near perfect. The complications come when the spin axis is not level, and this is still not complicated by more than 5% at extreme spin axis angles up or down. There is a centrifugal effect created by precession velocity around the precession axis, and there is another Coriolis effect due to the radius from the precession axis changing. There may be more complications, but I stopped looking. I accounted for these complications, and it made it more accurate, but my experiments were only using 240 frames per second, and I couldn't get any data fine enough to help piece this out more accurately. Then there's the fact that I'm not a mathematician, and it's just not fair that I spend so much time trying to figure this out when there are people with more math background that could immediately see different directions. I started to leave this out, but in this simulation there's more than one pivot, here and here. So the tilt direction and the center mass velocity vectors are not collinear. The light blue tilt vector is created by taking the difference between two velocity vectors located at different coordinates on the spin axis. The yellow and blue tilt axis vectors are merely rotated versions of this light blue vector, so they create the tilt axis in that way. The weight of this system is not affected throughout this simulation, so there's no mysterious lifting as Lathwaite alluded to in his video, because he called this the balance gyro, and it appears to have lifted in the process of reaching equilibrium. If you watch his video closely, he lets go of the weighted end before he lets go of the gyro, and this gives the weight a head start. It holds that position in the balance because that is where the tilt axis reaches an equilibrium condition. You can tweak the conditions to cause it to find equilibrium at any angle. It appears like the center mass is outward and it should create a higher torque on the balance, but the gyro is creating a torque that ends up being any force that stops the motion in the pivot points.